Okay, so now we're in our studio so that we can try some things out. I gave you this lab about multiple regression. Of course, we need our usual packages. And we're going to use this example data that I really like. It's from the General Social Survey, which is collected by NORC at the University of Chicago. It's a random sample of American households. It's been running since 1972. I just think it's an interesting way to look at data about the US, and I've given you just kind of a subset of questions, and I've done a little bit of data cleaning. So I gave you this file on Canvas. I would recommend you download it, put it into your same folder with all your other files, which should hopefully be associated with a project in RStudio. So then you should be able to read in this GSS data. So if you want to click on it, you can click and then scroll around and look at the information in here. It's got information like number of children, age of respondent, highest year of school completed, their father, their mother, their spouse, what their college major was if they went to college, if they got a high school diploma or a GED, their sex, the number of brothers and sisters. So there's just a ton of variables. You could also click the little down arrow to see the variables listed out here. So I sometimes do that if I know that it's going to be hard for me to remember how to spell the names of the variables. So I'm going to do just a tiny bit of data cleaning. So I'm going to do just a tiny bit of data wrangling. I'm going to make a new variable called age numeric, which is going to be the parse number of the age of respondent. So age of respondent is a character variable right now. So if I go back over here and try to sort by age of respondent, the least is 18 and the greatest is 89 or older. So it's not entirely numeric. And so what I'm going to do, it's a little sketchy, but I'm going to just pull out the numbers into a new variable called age numeric. And now that should be way over on the far side of my data. And the minimum will be 18 and the maximum will be 89. So just anyone who's over 89, I'm saying that they are 89. That's why it's kind of sketchy. But I wanted another numeric variable that was interesting, so I wanted to pull this one out. So we'll start by just making a ggplot. We're going to try and predict the highest year of school someone completed based on some other variables. So I could just look at this plot of the relationship between the number of years of school someone completed and the number of years of school their father completed. And then the question is, why is it in such like straight lines? And the reason is because school years are integers. No one said I completed 12.5 years. They either said 12 or 13. So I've got the integers here. If I wanted a little bit more of an idea of, there could be a lot of points piled up here, one approach to fix that would be to put a little bit of a jitter on my points. So if I run this code, now this adds a little randomness to both the x and y variables. So I can see that there are a lot of people who, it looks like, completed 12 years of school and their father completed 12 years of school. Everyone went to high school, right? But then there are fewer people who their father did 20 years of school and they did 8, right? There's just maybe one person there. Another thing that I could have done is change the opacity. So if I'd gone back up here, outside my AES, but inside my geom point, I could have put alpha equal to 0.4, let's say. And now the points are all piled up on top of one another, but I can see that these are really light and these are dark. Maybe I'd want to make it even less. Even less. Even less. So now I can really see where the data is, and then it's getting really pale out here. So that's just a little bit of a data viz idea. So we've got some idea that there's a relationship between this, right? As the number of years of school your dad completed goes up, we would expect the number of years of school that the person themselves completed would go up. So we could try doing a linear model. We're just going to do a simple linear regression. We're going to predict the highest year of school completed based on the highest year of school completed by their dad. And I could run M1, and then I could use this coef function if I wanted to. That just gets my coefficients. Or I could always do the summary of that model. These variable names are really long, so sometimes it makes sense to kind of squish over that pane and then rerun it so that I can kind of see everything on one line. So we were talking about inference. Here's my my t-value, 18.61, way off in the edge of the distribution, and R found my p-value, which is basically 0. So I would reject the null hypothesis. I would say it's looking like the slope for highest year school completed father is not 0. So I could say that. And then if we wanted to, we could make a different simple linear model using age numeric instead as our predictor. So I would encourage you to pause the video and try and make that model yourself and then come back and see how I do it. All right, I'm going to do it. So I'm going to do M2. It's going to be a linear model. I still want to predict that highest year of school completed. I'm just going to copy paste it by age underscore numeric, and my data is GSS. And then I could write a summary of M2. Then I like to do that command enter to just run one line at a time. I could look at this. Okay, age numeric, not significant in terms of predicting how many years of school you've gotten. That's kind of interesting. But I could still try and interpret the coefficient there if I wanted to. So for every year of age, I would expect the highest year of school completed to go down by 0.003 years. And if I wanted to compare two models between my previous one and this model, I could look at the multiple R squared, 0.17 versus 0.0053. This one's clearly worse. Usually if we're comparing models, we want to use the adjusted R squared. So I could have looked at 0.17 versus 0.0001. Again, this one is much worse. All right, so now let's try and make a parallel slopes model. I'm going to put in a new code chunk with this insert button, and I'm going to put in the born in the US variable. So that's a binary variable, yes or no. And I'm going to call this, I think, M3, and I'm going to try and do highest year of school completed by, and I guess I didn't specify which numeric variable I wanted you to use. Let's use highest year school completed father plus born in US. Data is GSS. And then we could look at the summary of this. So now I've got this born in US. It's got the yes stuck onto the end. R will always do that to help remind you which of the categories got baked into the intercept and which one has its own coefficient. So people who were not born in the US are baked into the intercept. The people who were born in the US, this is the coefficient. And this has changed everything about my model. So when I looked at summary M1, the coefficient for highest year school completed father was 0.29, and now it is 0.279. So it hasn't changed a lot, but it changed a little. And now I also have a coefficient on born in the US, yes. So if I had to interpret that coefficient, well, let's do each of them. So for a 1 year increase in the number of years of school a person's father has completed, we would expect the number of years of school they have completed to increase by 0.28 years, let's say. And then I need to put in a little bit more because this is multiple regression. So I need that holding all else constant, or holding their immigration status constant, something like that. And then to interpret the next coefficient, I would say compared to the reference group, compared to people not born in the US, we would expect, or the model would predict, that a person born in the US would have 0.66 additional years of school, holding highest year school completed father constant. So we want to compare apples to apples. So we're gonna, if we had people whose fathers had completed the same number of years of school, one was born in the US and one was not, we would expect the one born in the US to have a slightly higher number of years of school completed. So that's how we would interpret those two coefficients. And now we could do a prediction. Oh, I guess I did want you to use the age. Let's make that model then too. So I'll stick in this. Let's call that M4, and I'll use age instead as my predictor. So copy this. Instead of that, we're going to do age numeric. And then let's look at the summary of that model. Okay, so then I could do a predicted value based on my my model. So 12.88 minus 0.0047 times 57 plus 1.23 times 1, because it's a yes. And then I would predict they had completed 13.84, and I'll just put in parentheses 14 because of integers, 14 years of school. So I can just plug into multiple regression equations the same way I did for simple linear regression, but I have more things that I need to plug in. If I'd wanted to, I could have used the predict function. I could have done predict on that M4, and then I need new data equal to data.frame, and I need to put in an age numeric, 57, and I would need a born in US equal to yes. And that's just the more programmatic way to get that prediction. All right, if we wanted to, we could consider both the highest year of school completed by the father and the age numeric. I think I'm gonna change this, I'll make it M6, I guess, just to, is it M6? M5? M5, just to keep it consistent with my numbering scheme. All right, so now I've got some different coefficients, and then we could interpret those coefficients as well. So I'd encourage you to take a stab at this before you look at how I interpret the coefficient. Okay, so let's see. For a 1-year increase in the number of years of school completed by their father, we would expect a 0.31 year increase in the number of years a person completed, holding age constant. And then the same kind of thing for age. For a 1-year increase in age, we would expect a 0.02 year increase in the number of years of school a person completed, holding the highest year school completed father constant. And if we wanted to, we could start comparing the r squared, or we should really be comparing the adjusted r squared between these models. So I could look at the summary of my first model, had a 0.17. My second model was the bad one. My third model, 0.751, so that's an improvement. M4, oh, that was a bad one. And then M5. So I think it was between M3 and M5, and my adjusted R squared is the highest one I've seen. I'm explaining 18.51% of the variability, and then the adjusted R squared is also high. So this is a pretty good model for explaining the variability in the number of years of school completed. Then there's a question about the importance of these coefficients. So is highest year of school completed more important than age numeric? And is it fair to compare the two coefficients? And the answer is, like, we don't know. It is not fair to compare the coefficients because the data is not on the same scale. You know, age is going from 18 to 89, and highest year school completed father, that goes from, I don't know, 5 to 20, something like that. So a 1 year increase is a bigger percentage increase. So we can't compare those coefficients. We just have to say that, you know, they both look like they are significant. And now we could find the expected number of school years of school completed by someone whose father completed 12th grade and who is 57. Again, we could use that predict function. So I could predict M5. New data is a data.frame. And then I need to get my variable names exactly right. So I'll put this in by copying. It's equal to 12, and age numeric is equal to 57. So we would predict that person to have completed 14.29, 14 years of school. And then if we wanted to, we could find a residual. So I have just done this GSS, and then I'm going to filter my data for all the people who are 57 years old and whose dad did 12 years of school. So if I just ran this much, I'm going to get a bunch of data. So there's 12 people in my data set who have those characteristics. They're 57 and their dad completed 12 years of school. I just want to look at one person. So I'm going to slice off the first one, and then I'm going to glimpse, which is going to show me the data in a different kind of output. So now I can see everything about this person. They're, you know, row 195, they have one kid, they're 57, they completed 11 years of school, both their parents completed 12 years of school, they're male, they're retired, they were a pipe layer, plumber, pipe fitter, or steam fitter, they're married, etc. So we've got a bunch of information about them. And if we wanted to find the residual, we would have our observed number, which was the 11 that they actually completed, minus the predicted value. What did we find? 14.29. So the residual is negative 3.29. The residual, negative 3.29. So if we think about the geometric shape of this model, model 5 I was calling it, this one is the plane because it has two numeric variables in it. If I wanted to add that third numeric variable, or if I wanted to add that third variable, the categorical variable born in the US, yes or no, then I'd have parallel planes. So then it would be parallel planes in 3D. So let's try making that model. We'll put this in. I'm going to call this M6, and that's going to be a linear model. I'm just going to grab this much, and then I'm going to add in that born in US, and then my data is GSS. I could look at that summary of my 6th model. And it looks like all my coefficients are significant here. So I could interpret all those coefficients, or I could think about writing out the equations of the model.